Oh shoot. There we go.
All right, let's get started. We gotta finish week 4 and look at all the stuff we gotta learn today. It's like crazy today. Yes. Talk about what's the scores on your quiz? I only got halfway through them, meaning got 5 out of 10 problems graded, and I grade them like 2 problems at a time. So I look at the top 2 problems on everybody's, and I grade them exactly the same way. If someone got a point off for a mistake, it's the same exact point off on everybody's. Like, and then I go back to the beginning. I do the next 2 problems the same way, like a machine. So I got through. Was there 3 problems on the first page? The first problem on the second page, so that's 4 problems, and then the last problem on the second page, which was how many times, I think how the margin of error would be from the confidence or something like that, and the answer would have been 2, I believe. Is that the answer? Yeah. 2, yeah, and most of you got it. But, so I have all those done, and with those, half the quiz graded for everybody, it's, the average isn't bad so far. There's 3 people have a chance to have 0 wrong. I haven't made a mistake yet. So there may not be a curve if one of these 3, you know, ace it, which is most likely. I won't be able to curve it really. So we'll see. What? yeah. So here's where we're at. We just finished quiz 1, and on the second half of this week, we got hypothesis testing. This is like, you know, this is like one of the biggest lectures of the semester. I mean, this is what research is all about. This is what this class is all about, is hypothesis testing. Everything we've done in the first 3 weeks has been building up to these 3 weeks, next 3 weeks is what we've been trying to learn. I want to refresh your memory as to what the key item was that I taught you in the first 3 weeks. The key to recognizing one problem from another was the population and sample what? Standard deviation, or no standard deviation. Well, hypothesis testing is all about the same exact rule. Meaning there's one formula for hypothesis testing if you have the population standard deviation being given. There's another formula for hypothesis testing if the sample standard deviation is given. And there's another formula for sample or for hypothesis testing if there's no standard deviation because it's a proportion. Exact same scenario, exact same rule. Now here's the bad news. Too many of you are not recognizing the sample standard deviation and mixing it up with the population standard deviation. And you need to read more practice problems to get used to when is it really being described as a sample standard deviation and when is it really being described as a population standard deviation. It was, I think it was like problem number 2 on the quiz was supposed to be a sample standard deviation, but I was shocked. Was it 2 or 3? I can't remember. But I was shocked how many people thought it was population. So you were using the wrong Excel formula to find Z or T because you were using the opposite one. So what I'm trying to point out is to prepare for quiz 2, really, because quiz 2 is going to be all about hypothesis testing. And the way to recognize which hypothesis testing to use is the exact same rule you've been taught already. Does this problem have a population standard deviation? Does it have a sample standard deviation? Or does it have no standard deviation, which means it's a proportion? Exact same rule. You've got to get that down. Everybody in here, and it's not happening because, you know, yes, it's not most of you got it wrong, but too many of you mixed it up. Not only did you mix up the one that was sample, but then there was a problem. Was it on the second page, second one down, I think it was, maybe? No, it wasn't. It was on the first page, 3rd one down, the last problem. And it literally said the words, the population standard deviation is. And I was shocked at how many people use TIMD. But it said population standard deviation, the exact words. The word population was right next to the next 2 words, standard deviation. There was no way to confuse that with a TIMD. So something's still happening, and we've got to get through to everybody. So take these in-class assignments serious because, like today's in-class assignment, it's going to be obvious which one you're using, but look for the words because look at how it states the population standard deviation. That's what's going to be in this first week. is population standard deviations there. You know to use Z, and you're using the same Z formula we've been using for the first 3 weeks. I'm using the norm SIV because all we got to put in there is the confidence plus half the significance. We found Z. This is the formula. Next week, we're going to be doing hypothesis testing where we're given the sample standard deviation, and so you're going to use the T1, T.INV. But here's the deal. With sample standard deviation, it doesn't have the word sample right next to the word sample standard deviation, next to standard deviation, and that's what's confusing some of you. You gotta realize there was no comma in the sentence. What happens is it says, and the sample mean is with a standard deviation of. There's no comma there. There's no adding a word population. It was all in one sentence. It's describing the sample mean and the standard deviation. That's how you know it's a sample standard deviation. That's the trouble that's happening, is recognizing that it's truly describing the sample, but it doesn't have the word sample right next to it. That's next week again with hypothesis testing. Same exact type of words. It's going to have the standard deviation in it next week, but it's going to be in line next to as it's describing the sample mean. The sample mean is and the standard deviation, but it won't say sample standard deviation. It's still describing the whole sample in one sentence with no commas. That's how you know it's sample standard deviation. Population standard deviation kind of jumps out at you. It almost not always, but almost always literally says, and the population standard deviation, right there, the word right before standard deviation is right there, population. So that's how you recognize that one. And that's what's going to be in this week's homework. So let's look at this. Real quick, when's our next quiz? I want to make sure you guys are ready. It is October 17th. Going to be a Thursday this time. So the advantage of having it on Thursday is that I'll be able to grade it and we'll go over it Tuesday morning or Tuesday at the beginning of class. This time you got to wait all the way till next Tuesday to get it, which is rare. Usually I'm right there in the next class, but I could have been there too, and I thought, why am I pushing it? I can't even hand it back because the night class hasn't taken it. So, and even though the night class's quiz is different than yours, there's some similarities because I have to be fair that it's just as hard or just as easy. So there's some similarities, and they haven't taken it yet. So I got to wait till Tuesday to hand it back to you. So the next quiz isn't until October 17th, but it's going to come fast. And the next quiz is all about hypothesis testing, and it's going to have 3 hypothesis testing formulas, this being the first one right here, and it's all about you recognizing. Now here's the deal when the final exam comes. You're going to have problems on there about confidence interval, you have problems on there about hypothesis testing, and you got the same rule for both questions. You're going to say to yourself, okay, this is the confidence interval, oh, this is hypothesis testing. Now, am I being given the population standard deviation? Am I being given the sample standard deviation? Or is this a proportion and no standard deviation? The question's the same for each of those questions. And about probably a third of your final exam is confidence intervals and hypothesis testing. So if you get this down, recognizing that standard deviation, you will ace the final. A third of it. That's the key. If anything, the multiple choice should be the hard ones for you, not these problems. They're just like your homework. I don't know if you realize that as you were going through the test, you open up the homework answers, there should have been a lot of similarities because I'm writing them just like the homework. All right, so let's get back. You ready? Let's get started with this week. Here it is, one homework assignment. Both Excel and written's on the homework assignment. It's due next Tuesday, October 1st. October's here already, wow. There's the PowerPoint slides, 1 through 8, 13 through 22. There's the textbook pages. And of course, I'm recording this, and this will be up on Canvas hopefully tonight. Now, the homework. Don't leave it to the last minute. I think it's a little longer than the previous homework assignments you've had so far. So I would say give yourself at least 45 to an hour for this one, maybe a little more than an hour. The reason this one's going to take a little longer is because, is it 13 and 15? 13, well for sure 15, 17, and I think 13 too. I gotta stare at it for a minute. Yeah, all 3 of them are asking you to use the p-value approach. And many students find this the harder of the 2 approaches. Critical value approach of hypothesis testing, p-value approach. Critical value and p-value approach are for all 3 formulas that we're learning the next 3 weeks. Critical value and p-value. But p-value it just for some reason confuses a lot of people, so we're going to talk about it all 3 weeks though. But you have homework due next Tuesday where you literally gotta use the p-values. We gotta get there today to where you understand it. Here, let me, let's see, what am I? So you have what? This is just, I'm looking for you to write each answer in 1 or 2 sentences and just answer the question. I can't remember what it's asking. Now we wanna look. I'm sure they're easy. There's probably no way to get them wrong unless you skip them. Which reminds me, by the way, never, ever, ever leave an answer blank on the quizzes or the final exam. I am very generous with partial credit, but if you leave them blank, I cannot give you any credit whatsoever. Here's how you not leave an answer blank. You grab the numbers out of the question and you're saying, I can't answer this, I don't know how to do it. You grab the numbers and you start multiplying them, dividing them, adding, subtracting them. There is a ton of partial credit there for that effort. So that's how you take care of that. Never, from now on, never leave an answer blank. Anyway, so number 13, only do part A. The key here is you gotta give 2 Excel equations, I believe. Is each of these 2 Excel equations, I think? Because each of these, you gotta use either norm INV or norm SINV to find your Z, and then you're plugging your, and then you're finding your, this is your critical Z, then you're finding your calculated Z, and you're comparing the 2 Z's. That's what hypothesis testing is. Let me say that again, because that was kind of confusing. You're calculating a Z, but you still gotta find what's called a critical Z based on either the confidence or significance. Remember, if I say 90% confidence, what's the significance? 10%, very good, the opposite. Now we're getting into questions where you're being given the significance instead of the confidence. So realize you're being told the same thing, you're just being told the opposite. They're still the opposite of each other's. But you still gotta find what's called critical Z. So you're still using this formula for each of those last 3 problems. And you're using this because you're asked to do it manually. And this is to find the p-value. All right. Well, we got a lot of work ahead of us. We can tell, right, just by looking at it. Where are we going? We're going straight to hypothesis testing right here. Here's an example of what hypothesis testing is about. You ready? There's 2 hypotheses. There's the null hypothesis and alternative hypothesis. All right? Let me jump to a rule right here. This is so important. The null hypothesis is always the one that has the equal sign. The alternative never has the equality. It can have not equal to, but it will never have equal to. So let me put this a different way. The null hypothesis can have a greater than equal, a less than equal, or an equal symbol in the hypothesis itself. Let me show you what a hypothesis looks like so you have a good idea. Where is one? Oh, there we go. The null hypothesis is the top one. H sub O is the symbol for null hypothesis. This says the mean is equal to 3. Notice the equal symbols with the null. The alternative hypothesis is always the opposite of the null. So if the null is equal to, the alternative would be not equal to. But the null hypothesis could be greater than, less than or equal to. The mean is less than equal to 3. Notice the equal sign again is in the null. The opposite would be, the alternative would say greater than. Now the null could be greater than equal to. Again, the equal sign's there. The alternative in that case would be less than. Whatever the null is, the alternative is the opposite with no equal symbol. Boy, I was flipping through one of those social net things, either with Instagram or TikTok or one of them. And there was an advertisement for this little square thing, trying to get students to buy it. I didn't see the price, and I should have. Where you just turn it on, and I guess it has a huge amount of storage, and it will just listen to all the lecture and all the conversations or any meeting you're in. And then at the end, it's hooked up to the internet through artificial intelligence. It will take and write all the notes from all the lecture. It will put dots next to the main subjects, and it will summarize at the end and let you know what you need to do to prepare. Anybody ever seen those, or am I the only one who saw that commercial? Huh? No, I didn't save it. It was the second one I seen, so I usually see these things like 10 or 20 times. But I thought, you know what, that might be useful. I would stop taking notes if I had one of those. I'd just sit there and listen. I mean, why write notes if this thing's taking all your notes for you? And then you just email it to yourself or transfer or whatever if you want to print them. Or you have it digital, you can use it while you're taking a quiz. Let me get one of those for each of you. Just checking, that was a joke. All right, let's keep going. Was I recording that? It was a joke. Wow. All right, you ready? Here's an example hypothesis. You're working at a cell phone company and you guys are bored because no customers come in all day. You say, let's try an experiment. And someone says, hey, I think everybody who works at this mall, let's say you're at a mall, there's 100 employees. And someone says, I'll bet you that the average monthly cell phone bill for all the employees at this mall is equal to $42. There's the null hypothesis, the assumed, what you're assuming. And now you're saying, no way, there's no way the average of the cell phone bill is $42. Matter of fact, I believe it's something different than 42. Now, I'm not saying 43 would be different or 41 would be different. I'm saying it's going to be so different that we can be out here in these tails. It's going to be so different. So in the center here would be $42. And then we're going to figure out the confidence range. And on the outside of the confidence range are the two significance. Why is there two of them? Because this is equal to, and we're saying it's not equal to. You as the researcher, the one who's arguing the premise that the average cell phone bill is $42, you're hoping that when you collect your data, that it ends up being either way below $42 or way above $42, because if it's way out here or way out here, you've proven there's no way it can be $42. You're wrong. But if you take a sample, you can't go talk to all hundreds of them, let's say a couple hundred, you're just going to get a sample of 30 people and find out what their monthly cell phone bill is. And you do that, and it's maybe a little below 42 or a little above 42, you did not prove it. You're so close to 42 still that maybe if you had time to do all of them, it could be around 42. So you didn't prove anything. For you to win the argument, your sample has to be so far away from the assumed $42. The null is always the assumed hypothesis, the one that everybody's always believed, and you're trying to prove wrong. The alternative is what you're trying to prove, that because you believe the null is wrong, that what everyone's believing can't be right. That's what true research is all about, is that you're discovering something new, that you're saying, no, this assumption you're all making is wrong, and I'm going to prove it. And you're proving it without a shadow of a doubt. You're way down here. Now, look what happens. If I said to you, okay, we got this bet. You get $42, and I get numbers way below or way above 42, but how important is this? Give me at least a break. How about if you give me, now think about it, the person who says, yes, the average price is 42, we're going to assume that, let's give them 90% of this bell curve, right? That's 90% confidence. So how much will be in each tail? Let me repeat that. The person who says, hey, the average cell phone bill is $42, we're going to give them 90% of this. Whatever the numbers are that go above and below 42, that equals 90% of the center. How much, what percent's in each tail?
5.
Exactly. 10% is the significance, divided in half, 5% in each tail. You got it. All right. But this person could argue and say, no, this is really important. I'm not giving you 10%. I only want to give you, I want 95%. You only get 5%. Okay, so what happens in that argument? We're going to give into it because we feel confident it's not $42. But what's going to happen is, now we've just given that person a wider range. We went to 95%. And now, what do we have in each tail here now? 2.5%. That's all we have because there's only 5% significance. We made it tougher for us to prove it when we take a sample of at least 30, the average cell phone bill is not going to be $42. We made it tougher on ourselves to prove our point. But if we're in those tails, we've definitely proved it. Now, the reason I'm bringing this up is because that's how they decide how much significance or confidence to use based on how important this research is. Meaning, for example, let's say a pharmacy is paying us independently to test a drug. And what this drug is doing, the effects this drug is doing, has to have an effect on whatever it's supposed to do, so much so that in that kind of research, the null hypothesis is that this drug won't do anything. And we're going to give them 99%. That for this drug to be given to the general population, it's got to be so far away from doing nothing from one patient to the other. Don't forget, there's a group of patients who think they're taking the drug, but they're really not. And there's a group of patients who are really taking the drug, and they all have the same illness, whatever it may be. And the difference of how these pills are affecting them has to be so large that you have to be in the, let's see, if it's 99%, so what do I have in each tail then? 0.5%. That's it. That drug, what effect it has on the people who are taking the drug, that effect has to be so much different than those taking a fake drug, a placebo it's called, that we only get this 0.5% in each tail, or this drug's never going out to the public. The federal government will not allow it to be experimented on the public unless it passes this kind of research, with only like a 1% or less chance of that drug is proving to do what it's supposed to do. Because that's really important. But arguing about a cell phone bill average cost, we'll use 90% and 10%. We'll give a chance. It's not so important. If we're in the 5% one way or the other, then yeah, we're proving it. The cell phone bill is not average $42 among everybody in the mall. So you're getting it, right? You realize how it works? Now, I want to point out a symbol that will not be on your next quiz. I will say the word somewhere in there, but that stands for population standard deviation. Or wait, is this proportion? Oh, that's proportion. We're not doing that one yet. Here's the mean. We gotta get to the standard deviation. This is the mean we're assuming, $42. We're not doing the proportion this week, ignore that. So there's the $42. Now here's the hypothesis. The mean's equal to okay, well here's another example. States claim, assertion tested. The average number of TV sets in U.S. homes equal to 3. Here we go, U.S. homes. Think about how many there are. We don't have time to call every single or knock on the door of every single U.S. home, so we're going to take a sample. Since it's such a huge population, we'll use a big sample size. Of course, we're going to calculate what the sample size should be. Let's say we do 90 households, and we ask them how many TVs they have. What's the alternative hypothesis? The hypothesis we're assuming is the average amount of TVs in homes is equal to 3 TVs per home. What's the alternative? Not equal to 3, exactly. Not equal to 3. All right, here we go now. We gotta switch it. Let's say this said that the average amount of TVs per home is equal to or greater than 3. 3 or more, like greater than or equal to 3. The alternative then would be that the average amount of TVs in the US homes is less than 3. Notice it doesn't have the equal sign in that alternative. But here's the deal. Let me get to this slide. Whoop. Here we go. Here's the deal. Let's say I said 90% confidence. You told me that's 10% significance. And then I said to you, if we said the average amount of TVs per home is 3, the alternative would be the average amount of TVs is not equal to 3. 5% would be in each tail because it's 10% significance. But if the null hypothesis said the average amount of TVs is, I'm going to this one, greater than or equal to 3, the alternative is less than or equal to 3, our alternative is down here in one tail only. It's a one-tail test. This is called one tail because the alternative in the null is including a tail, and the alternative is in one tail only. But we're still being told 90% confidence, 10% significance. Here's the deal though. Now, because it's a one tail, you don't split the significance in half. All 10% is in one end. Up there, we had to split in half, 5 at each end. Down here, all 10% is there. If it says 90% confidence, that tail equals 10%. Up here, this is, hey, there's less than equal to 3 TVs. No, I believe there's more than 3 TVs. All the significance is in the upper tail. If it's 90% confidence, 10% significance, that's 10%. You have to be able to read the problem to know the difference between, where is it, one tail and two tail, because when we get to the point to where you're calculating p-value, based on whether it's a one tail or two tail, you gotta know if you're multiplying this result by 2 or not. If the problem is a two tail, this p-value calculation has to be multiplied by 2. If the problem is a one tail, you do not calculate this by 2. Want me to repeat that?
Yeah.
Okay, you ready? At the end of this lecture, it's all about getting to this p-value. All about calculating this probability, the number from the significance type thing, all right? That p-value has to be multiplied by 2 if the problem is a two-tailed problem. I almost want to open up the homework. Let me read one of these so we can tell if it's one tail or two tail. Ready? Consider the following hypothesis. A sample of 25 observations yields a mean of 13.4. Stop. The null hypothesis, the mean is less than or equal to 12.6. The alternative hypothesis, the mean is greater than 12.6. Is this a one tail or two tail? One. Exactly. Because it's a one tail, let's look at the confidence or significance. 10% significance. How much is in each tail?
10%.
There's 0 in one tail and there's 10% in the other tail. All of it's in one tail because this is a one tail.
How do you know?
Well, based on that alternative. If the alternative says greater than 12/16, then the tail is in the greater than, in the above 0, up here. If the alternative says the mean's less than a number, then we're talking about the significance being down here. So it's all about I look at the alternative hypothesis to know which tail has that significance. Everybody see that? Let me do one more here. What's the other problem in our homework? What number was it? Nobody knows. Hang on. It was number 15. So let me do 15, hang on. Let's read this real quick. Oh, this is too easy. What was the next one? These are all too easy. None of these are stories? Okay, let me do 15 then. You ready? Consider the following hypothesis. One tail or two tail? 19 at the bottom there. Two. I'm right here. If this were equal and not equal to, it'd be two tail. This is greater than equal and less than, so it's one tail. Let me repeat that. If this were equal and not equal to, then it's two tail. But because this is a greater than equal, it's a one tail. There's one tail. Now, is the significance on the bottom of the bell curve or on the far right? On the left or the right based on this alternative? Say it again. It says the alternative hypothesis is that the mean is less than 150. Look at it. Where is it? Less than. That's right. It's down here. How much significance is down there? Where is it on here? We gotta go up to the top. Darn. Hang on. How much? Where's the significance? We're doing A or B. I don't know. Let's pretend we're doing A, even though I don't know. No, we're doing B. How much significance does that say? In B, 1%. Where would the 1% be? Is it a 0.5% and a 0.5%? Or is it just a one tail? One tail down here. The whole thing's there because it's a one tail. If it were two tail, half of it would be in each tail. You get it? All right, let's get back to this. The most common significance you're going to see on these problems are 1%, 5%, and 10%. The opposite of this would be 99% confidence, 95% confidence, 90% confidence. This now we're just getting into where you're being told the significance instead of the confidence. That's all. Don't let this fool you. All right. There are two types of errors. I'm not going to go into calculating a type 2 error today at all because it's really a difficult calculation. But a type 1 error, I need you to know the meaning of these, is to reject a true null hypothesis. Rejecting a true null hypothesis. That the null hypothesis is true, but we rejected it because our results were way down here or way up here, but we shouldn't have rejected it because the null hypothesis was really true. That's called a type 1 error. Type 2 is the opposite. It's where you fail to reject a null hypothesis when really it was false. So our sample means were too close to the center and we didn't reject it, and really we should have rejected it, but something happened when we took our sample. Maybe it was in the procedure we used or something. So that's called a type 2 error. What's important here is for you to be able to distinguish the difference between type 1 and type 2 error, what it means. That's what I want to point out for you. All right. Here we go. Here's the testing. We're doing hypothesis testing for a mean when the standard deviation of the population is known. Let me repeat that. All we're talking about is when the population standard deviation is being given. Just like week 1 for confidence intervals, when the population standard deviation is given, which means we're going to use a Z formula. Next week, that right-hand one right here, where it says this population standard deviation is unknown, that's going to be a sample standard deviation, and we're going to use T, just like in week 2 for confidence intervals. So we're using Z. Now here comes the formula. There it is. Now let me put this in words. This is called Z calculation, because we're finding our Z based on our results. And our Z is going to be somewhere between -3 and +3, most likely. Don't be wrong, it could be smaller or bigger, but most of these always land between negative and +3 because they want to be on the bell curve. All right? So there's our Z. Now in words, on the left-hand side of the numerator is the sample mean, not the hypothesized mean, the sample mean results. That's the left-hand side of the numerator. This determines whether you're going to get a negative or a positive result. The left-hand side is the sample mean. The right-hand side is the hypothesized mean. What's being told to you in the story. Then the sample mean is being given, that's the left-hand side. The hypothesis is the right, the sample is the left. There's going to be a difference between them. That gets divided by the given standard deviation, which is going to be the populations of this week, divided by the square root of the sample size. This should look familiar. This is the same as confidence interval here in the denominator. The difference is the numerator. That's the only difference this week. The denominator, standard deviation, divided by the square root of sample size, has to be done first before you divide into this numerator. Order of operations, all right? Don't divide until you get this done. Subtract the top. That's why I put it in parentheses. You've got to subtract that top before you divide. In order of operations, you're supposed to divide before you subtract, so I'm throwing parentheses around here to try to get you to understand you need to subtract before you divide. Does everybody think they got this formula down? This is the main formula. So you're going into the first problem, right? And you are going, okay, I'm going to set this up. Well, here's our hypothesis mean. It gave us the population standard deviation. It told us the sample size. Oh, look at this. It's given us the sample mean result. Now we got to calculate our Z. To use the critical value approach, we have to calculate what's called a critical Z and compare the two. Let me stop there. For our homework, we have to use what's called the p-value approach. So we're going to use, once we have this Z, let me point this out, once you manually calculate the Z, you plug it in right there. Look at this formula. Equals norm dot distribution, the Z value you just calculated, comma, 0, comma, 1, comma, 1. Always. Let me say it again. You guys ready? The p-value approach is you manually calculate that Z right there. You plug that Z into this formula, equals norm dot distribution, Z value that you just calculate, comma, 0, comma, 1, comma, 1. Some people will put a 1 minus in front if that ends up being positive, and some people will leave it off. If that ends up being negative, you'll get used to this. You got to practice a few of these. Then this result is compared to the significance. That's called your p-value. This is your p-value calculation here. This is if you're using critical Z approach. P-value approach, critical Z approach. The homework, p-value approach. But you've got to manually calculate that Z. Here's an example. Where are we at? The TVs. Let me go back to the TVs. Is this it? The average number of TV sets in U.S. home is equal to 3. The null hypothesis is going to be that it's equal to 3. The alternative is going to be it's not equal to 3. So there's that. Did we get the standard deviation somewhere in here? Let's see. Okay, let me get to the calculations. So here we go. Test the claim that the true mean TV sets in U.S. homes is 3. Assume the population standard deviation, I'll use words, but that symbol is population standard deviation is 0.8. So where's my pen? So this is going to be So all we have right now is something minus 3 over 0.8 over the square root of our sample size. It says state the appropriate null and alternative hypothesis. The null hypothesis, the mean is equal to 3, because the statement said the average amount of TVs in US households is going to be 3. The alternative hypothesis is that the mean is not equal to 3. The opposite of whatever the null is. Specify the desired level of significance for and the sample size. For this particular experiment, we're going to use 5% significance. All right, let me put it here. 0.05 significance. Our sample size is 100, so this is the square root of 100. Now all we need is our mean result. Here we go, we're getting a hold of 100 households. Hey, can you tell me how many TV sets you have in your house? I'm doing an experiment, I need to do some research. Thank you very much. 99 more to go. Hey, can you tell me how many TVs you have in your household? Boom, we got the result from 100 homes. And the average is, now this is where we're at right now, we got everything here except for this number here. This is gonna give us our Z. Let's go to the next slide. And we go ahead and call the homes, and there were 2.84 TVs in our sample. The mean number of TVs per household in our sample was 2.84. All right, let me put parentheses around this. So now we take 2.84 minus 3, gives us a negative 0.16. We divide by, you ready? Square root of 100 is 10. 10 into 0.8 is 0.08. So now we end up with, I want to write that down, negative 0.16, is that what that is? Divided by 0.08. And this ends up being negative 2.0 on the nose. Wow. That's our Z. All right, I want to stop there. This is half of the homework right now. What I just did, you look at a problem, you saw the hypothesis and the null hypothesis. You now are going to set up this formula, because in each of the problems, I'd say do an A or B. It's going to give you the standard deviation. It's going to give you the sample size. There's my setup. I calculated Z 2.0. There's my calculated Z. Now, on a test, you're either going to be asked to use that Z you just calculated and tell me whether you reject or not reject the null hypothesis based on the critical value approach. Or it will say, take that Z you just calculated, negative 2.0, and tell me whether you reject or not reject the null hypothesis based on the p-value approach. Now let me clarify what I mean. The null hypothesis, let's go back to it, is that the average number of TV households equal to 3. If our results, 2.84, is too close to 3, what was this? Well, it was the significance was 5%. And this is a two-tail, right? So 95% in the center. Whatever that lower confidence number is and that upper confidence number, if 2.84 is between them, you gotta write a sentence that says, we can't reject the null hypothesis. 2.84 is too close. You don't have to write that down, but you're saying we can't reject. The only word you need at the end is, are you rejecting or not rejecting the null hypothesis? That's your answer. Let me say it again. You're either rejecting or not rejecting the null hypothesis. You do not say, oh, we're accepting the null hypothesis. Oh, we're accepting the alternative. No. You're either rejecting or not rejecting the null hypothesis, the assumed, the every day, all this time we've been thinking there's 3 TVs in the household. You're either rejecting it or not rejecting it. Here it is. If 2.84 is too close to 3 TVs are null, we cannot reject it. We don't have evidence to prove that wrong. Yes, 2.84 is not 3, but it's too close to 3. We can't reject 3 TVs. But after we do our math, if 2.84 is out here in this tail, below that lower limit, if we did a confidence interval, if it's out here in the tail, we have evidence to reject the null. There can't be 3 TVs. We have evidence to show there's got to be less than 3 TVs. That's what our 2.84 says to us. Do you get it? All right. Now, let me What I just described to you is called the critical value approach. I want to say it again using statistics. You're about to calculate this z, or really this z right here, negative 2.0. And you're comparing it to what the upper and lower confidence interval would be in the form of a z though, not numbers, in the form of a z. So here, you ready? What would be the critical z if I said to you 5% significance? This is your critical z. Help me out. Equals norm dot s dot I and v parentheses. What is my confidence plus half significance? That goes right there. What is that number? Very good. Woo! 0.975. Because 5% significance means 95% confidence. Half of that significance would be 2.5%, which is half of 5. Added to 95 is 97.5. Tell me what this equals. Where is my Excel? Come on. Where's my Excel? Tell me what this equals. Norm S I and V. Okay, all right. Hang on, I got it right here. Oh, I heard someone. No.
1.955.
Is this it right here? Here we go. Norm S I and V 0.975. 1.9599. We're going to say 1.96. We're going to go 1.960. All right, here we go. Where is both? This is a two-tail. So that's positive and negative 1.96. Are you ready? 1.96 positive is about right there. 0, 1, 2, 3. Negative 1.96 is about right there. Hang on. There it is. Now, where did our z we calculated land? In between those dots or outside of those dots?
Outside.
It did. Negative 2 is outside of negative 1.96. If your calculated z is outside of the critical z, you have evidence to reject. If your calculated z is inside the critical z, you cannot reject the null hypothesis. Everybody hear me? So what words would you give me at the end of this problem? Would you reject or not reject the null hypothesis? Reject, because negative 2 is outside that right there, which is negative 1.960. This is positive 1.960. And that negative 2 is outside of it that we calculated. You just did the critical value approach. All right, we're doing the same problem, but p-value. Look at us. We went through a lot of hard stuff in a very short period of time, so we're going to do another example. But here we are, we're on the last part. This is the key to doing your homework right now, what I'm about to say. This is how you calculate p-value. Here's the deal. What's our significance? It's what percent? 5%. If your p-value, why am I writing this on here? Hang on, it's right here. If your p-value is less than your significance, you have evidence to reject. Here's p-value. If your p-value is less than your significance, you reject the null hypothesis. If your p-value is greater than or equal to, look at where the equal part is, you cannot reject. You ready? We're about to take our z we just calculated. So for the homework, you had to do exactly what we did here to get to that z, but instead of using critical value calculation, you're now going to plug it in here, and you're comparing what you're about to calculate to the significance of 5%. Here's my question though. At the beginning of this lecture, I said you have to do something special when you're calculating your p-value based on whether this is a one-tail or two-tail. The TV question, is it a one-tail or two-tail? What's the average number of TVs per household? 3. Less than 3, greater than 3, or did it say equal to 3? Equal. Makes it one-tail or two-tail? Two-tail, which means what you just calculate here, you have to multiply by 2, then compare it to that 5%. You only got to do that last step, taking this calculation multiplied by 2 if it's a two-tail problem. Here we go now. I'm gonna punch it in. Let me get my Excel. Boom. And here we go. Equals. What is it again? Now remember now, you may, if you have a positive z, you may need to put a 1 minus in front to get the because if I don't put a 1 minus in front, I'm really getting the confidence and not the significance. So watch what happens. If the number's really big, then you go, oh, I must have had a negative z, or a positive z, I'm supposed to put a 1 minus in front. But this one's a negative z. So here we go. Equals norm dot distribution, parentheses. I'm putting in the z value we just calculated, which is negative 2.0, comma, 0, comma, 1, comma, 1. Parentheses. 0.02, just a little more than 2%, but we're not done. If this were a one-tail, we'd be done. We'd write this equation down and the result on the paper, and then we say this number is either less than or not less than our significance, and then we reject or can't reject. So help me out now. Is this number 0.0227575 less than 0.05? Yes or no?
Yes.
It is. And when what you just calculated p-value is less than your significance, you must reject the null hypothesis. If this is one tail, you just did it, you're done. But this isn't one tail. We've got an extra step to do. We gotta take what we just calculated and multiply it times 2. So I gotta take, what is that cell? That is G15. You could do, you know what, there's so many different ways to do this. I'm just gonna add times 2 right in the formula itself. Times 2. Here we go. Now, here we go. Look at it carefully. We're comparing it to our significant 5%. All I want to know from you is, are you rejecting or not rejecting the null hypothesis? I heard it.
Rejecting.
It is rejecting. Because 0.04, I can't read it, 55?
Yeah.
0.0455 is less than 5%. Since your p-value is less than 0.05, is it less than equal? I can't remember, but since it is less than 0.05, you must reject. Reject. Oh my God. That's it, we can go home. Oh my God, was that a ton of information. How do we feel? Can we do this? You ready? You ready to do another? You don't want to do another example? Seriously?
No, yeah.
What do you mean? What time is it? We got time? Let's do another example. Let's do one of these non-homework problems. Let's do number 14. 14 part of our homework. I don't think it is. Let me look at my notes. I don't remember if we're supposed to, I don't know if I planned a second one or not.
Will the problems tell us whether to choose like the critical or the p-value?
Yes, it tells you, and I think they all say, I believe I tell you in the instructions of the homework to do, let me look again. It says, do 13A, only part A, show your calculation details, make sure and state if the null hypothesis can be rejected or not, give the Excel equation and result to find p-value. So in the instructions for 13, 15, and 17, I'm asking you to find p-value in my instructions. You're just getting the information from 13A, 15A, B, whatever else there is, 17A and B. You're just getting the information from those, but you're doing these instructions, which is p-value, what we just learned. So we're gonna do, right now, we're gonna do 14 p-value. Are you ready? Okay, there it is. Where is it? Let me get it up here. Can everybody see it? Can I make it brighter? Hang on. There we go. Look at 14. Stare at it. Answer this question. One tail or two tail? Two it is. Two it is. Why? Because it's what? Equal and not equal. Very good. There we go. Null hypothesis is equal to 100. The alternative hypothesis is not equal to 100. A sample of 16 observations. Hang on. We got to get started here. So 16 observations. I'm right now. Hang on. We're changing all these numbers. 16, is that what it said? 16 is our sample size. Let's keep reading. A sample of 16 observations yields a sample mean of 95. This is our left-hand side of the numerator, 95. There's our null hypothesis that says 100. There's our right-hand side of the numerator, 100, because that's the hypothesized. Then it says, assume that the sample is drawn from a normal population with a population standard deviation of 10. population standard deviation equal to 10. 10 divided by 4 into 95 minus 100. That's a negative 5 over 10 divided by 4, 2 point something, whatever that equals. Somebody get a calculator up. Help me out here. What's 10 divided by 4?
2.5.
Is it 2.5? Why is it on my calculator right now? How did that happen? I must have did this already. I don't know. What was this? This is, oh, not 10 divided by 4. Oh, yeah. My bad. 2.5, you said?
Yes.
Okay, now 5 divided by 2.5. Is the answer here negative 2.0?
Yeah.
Seriously? It's the same z? We got z at 2.0, negative 2.0 again on 14? Well, how crazy is that? What significance are we using? Let's use C. Go C. What significance are we using? 10%. Uh-oh. 10%. We didn't have 10% last time. Let's plug it in again. We're doing p-value. We're plugging in the negative 2 here. We did this whole thing again, and we ended up getting times 2, if I recall. We ended up getting, what wasn't we? 0.0455? 0.0455. Let me repeat what I just said. This calculated the negative 2, just like the example problem from the PowerPoint. And then we put it in there as negative 2, 0, 1, 1, times 2 though, because you said it was a 2-tail. We get 0.0455. The significance is 10%. Noah will tell us, are we rejecting or not rejecting, Noah?
We're not rejecting.
I can't hear you.
We're not rejecting it.
Because the significance, where is our calculation again? Because we got 0.0455, and the significance is 0.10. Is 0.0455 less than or greater than 0.10?
Less than.
And any time your p-value is less than the significance, you must reject. You must reject. You must reject. This is easier to reject than the last one. The last one we were using 5% significance. That's the only difference between this problem that we just did. And we're comparing the exact same p-value because it was a 2-tail and we calculated it at negative 2.0. But everybody see the process? You calculate your z, you're gonna plug your z into this equation to get your p-value, and then you compare the p-value to the significance. And if your p-value is less than, I wanna make sure I get this, is it less than equal or just less than? I gotta try to remember. What, did it say less than equal? Let me get back here. Here it is again. If your p-value is less than your significance, you must reject. But if this p-value is equal to or greater than, you cannot reject. So be careful. If they're equal, you can't reject. It's gotta be less than. It's gotta be less than. We got time for one more. We got homework due in 5 days, so we should do one last one. Let's go back to the book. Let's just go down to the next problem. That's not part of our homework. If there is one. Let's see, 15 is part of our homework. Let's go to 16. Whoops. 16, can we do this one? A researcher wants to determine if the population mean, hang on a minute, if the population mean is greater than 45. Okay, this is being given to us in words. This is perfect. You now need to write the null hypothesis. Hang on, let me put it up here. H sub O is your null. H sub A is your alternative. There's your alternative. I'm going to read the sentence out. A researcher wants to determine if the population mean is greater than 45. Boom, right there. The researcher is saying, hey, it's 45 is what we're assuming. Whatever it is we're measuring, 45 is it. So tell me what the null hypothesis would be. Ready? Is the mean, I'm just putting the word mean, and this one would be mean. Okay, in the null hypothesis, what would be the symbol there? Greater than equal, because the researcher wants to know if the population mean is greater than 45. But you gotta have the equal symbol. So we're gonna go with greater than equal 45. And if we're real technical, we might go with 46, but stick with, we're not trying to make this hard. Based on the word. 45, so what would be the alternative? Less than 45. The equal has to be there. Yes, there's for sure on your next quiz where you're going to be given a problem and you have to give me the null and alternative hypothesis, just like we just did. And it's all about you having that equal symbol in the null.
It always has the equal symbol?
Always in the null. It either is going to be equal to, greater than equal to, or less than equal to, but it will always have an equal involved. All right? Now we have our hypothesis. All right? Let's look at the other numbers. Get ready to set this up. Hang on, we already know one of these numbers. Let me get this all erased here. It says the null hypothesis is 45. So there's one of the numbers right there. Let me keep reading. The researcher wants to know if the mean is greater than 45. A random sample of 36 observations yields a sample mean of 47. Here we go. The sample mean is 47, and the number of observations was 36. So the square root of 36 right there. All we need now is our population standard deviation. Let's keep reading. Assume that the population standard deviation is 8. Okay, math, where you at? First of all, square root of 36 is 6. So 8 divided by 6. Someone give me that denominator. That's 1 point something. 333. 47 minus 45 is 2. 2 divided by 1.333. Now, this is good. This is our first positive calculated z. You're going to see what happens when we put a positive number in here. You're going to get the opposite of the p-value, which means put a 1 minus in front, or just realize you're going to get the opposite, because we got a positive number. What's 2 divided by 1.333333?
1.538.
5 what?
38.
38? Seriously? 1.538 is our z.
If you round to 3 digits, it's 1.500.
1.5 what?
00. If you round to 3 digits.
It's 1.50038. So 1.
Oh, I see what you guys are saying. Well, I'm going right there then. How's that? Should I go one more? So you're saying right there, oh no, that'd be 4.
It would be 4.
Like this, 1.5004, you wanna do that? I'm not gonna be that picky. If you notice, oh, I haven't back to quizzes yet. I can't tell you how many of you didn't go 3 digits on that quiz, and I didn't take any points off. But consider this a warning. Oh my God, you guys are driving me crazy. You know how much grading I gotta do this weekend? The rest of all your quizzes plus the night classes quizzes, which is a different quiz. This is crazy. Who does this? All right, here we go now. I'm doing p-value.
Just 1 0.
What do you mean just, oh, there's only 1 0? Okay, hang on, we're switching this again. 1.504.
No. 04. 004.
004, who said this?
Mine is
So, somebody check, are you using enough threes? Did you use 1.33333?
I use 3.
So, what is it, you guys?
1.5004.
004. Okay, are you ready? We're gonna do our p-value. Here we go. We now have our z. Equals norm dot dist parentheses 1.5004 comma 0 comma 1 comma 1 parentheses. Okay, here it is. We have a positive number this time. What this is going to come out with, because we have a positive z this time, is really the opposite of the significance. Look how big that number is. Oh, why didn't you guys tell me? Darn. Oh. Okay, let's go back. Here it is. Equals normal distribution 1.5004 comma 0 comma 1 comma 1. Look what it came out to. So really, the p-value is the opposite of that. So watch what I'm going to do. I'm just going to put 1 minus in front, just to find the opposite. There's our p-value. Now, do we compare this to the significance, or do we multiply this times 2? Look at this over here, you guys. Do we compare it or multiply times 2? Hang on, Nick, I heard you. I'm sorry?
Compare it.
That's right. Correct, everyone. Compare. There's no reason to multiply times 2. This is a 1-tail, not a 2-tail.
Why'd you do 1 minus?
Only because this came out to a positive 1.5 instead of negative. So when you put a positive number in here, you're really finding the confidence instead of the significance. So I wanted to find the opposite. I put a 1 minus there. Or I could have made this negative 1.5. That would have done the same thing. I could have either made that negative or put 1 minus there. I just want to, because I know that when this comes out to a positive number, you put it in there, you're finding the confidence when you really want the significance, the opposite. So here it is. I'm now going to compare that to the significance in the problem. I don't remember the significance in the problem. It said use 5% significance. So look at that carefully. Look at it carefully. It said use 5% significance. My question for you is, do we reject the null or not reject the null? I heard it over here somewhere. That's right. Because look at 0.06 whatever is above 0.05. We can't reject. The p-value has to be less than the significance, not greater than. We cannot reject. I want to make sure you realize the homework specifically says on 13, 15, and 17 that you got to tell me if you're rejecting or not rejecting once you find that p-value. Show that you're comparing it to significance and tell me if you reject or not reject the null hypothesis. How do we feel? Can we do this homework? All right, good luck. Have a great weekend. Oh my God, we made it. Look at nobody's moving. They're all stunned.